Hi class, we are now beginning chapter 9. This is 9.1, covalent molecules. In this lesson, we're going to explore the structure of covalent molecules. Remember that in a covalent bond, two atoms share electrons. Covalent bonds occur between nonmetal atoms by sharing electrons. So these atoms are often able to fill their valence levels and satisfy the octet rule. Recall that the octet rule states that atoms are stabilized by completely filled S and P sublevels. This corresponds to 8 electrons in the valence shell. For example, if we look here at chlorine gas, each neutral chlorine atom has 7 valence electrons. By forming a 2-electron bond, both chlorine atoms fill their valence electrons. So both have only 7. They have a space for one more. So what they do is each one has that one, shares it with the other one, and now they have it filled. So this type of drawing is called a Lewis structure. In Lewis structures, we use a dash to represent shared electrons. And this is more like housekeeping. It looks cleaner. You can see what's going on. When you have a lot of dots, it gets really messy and complicated to really understand what's going on. So we use a dash in the form of the 2 dots so you can see that that's a bond. But this is always 2 electrons here. So Lewis structure shows the arrangement of covalent bonded atoms, and we use the dash for the representative of the bond. Sometimes atoms share 2 electron pairs. This is called a covalent double bond. We can see an example of a covalent bond with molecular oxygen. Each oxygen atom has 6 valence electrons and therefore needs 2 additional electrons to fulfill the octet rule. Similarly, atoms can share 3 pairs of electrons to form a covalent triple bond. This type of bonding occurs in a molecule of nitrogen gas. Each nitrogen atom has 5 valence electrons and therefore needs 3 additional electrons to fill its valence. The nitrogen atoms form a triple bond. Notice these Lewis structures also show the unshared valence electrons. Although unshared electrons do not form bonds, they do have an impact on the shape of the molecule, which is what we'll eventually get to in this chapter. Because electrons pair up with opposite spins, we typically represent unshared electrons in pairs. For example, in the Lewis structure of chlorine, each chlorine atom has 4 pairs of electrons. 1 pair of electrons forms a covalent bond. The other 3 pairs of electrons are unshared. Chemists refer to pairs of unshared valence electrons as lone pairs. We can think of an octet as 4 pairs of electrons. In most covalent molecules and polyatomic ions, all atoms follow the octet rule. For example, consider the Lewis structure of carbon dioxide. In this molecule, the carbon atom forms 4 covalent bonds. This means that there are 8 valence electrons around the carbon. Each oxygen atom forms 2 covalent bonds and has 2 lone pairs. Each oxygen atom also has 8 valence electrons. Both carbon and 2 oxygen atoms fulfill the octet rule. So whichever ones you count, we count 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. So this has an octet, this has an octet, and this has an octet. Okay, as a second example, let's look at water in the Lewis structure of water. Notice that the oxygen is surrounded by 8 valence electrons, a complete octet. Each hydrogen only has 2 electrons, the covalent bond. Because only 2 electrons are needed to fill energy level 1, each hydrogen in this structure also has a complete valence, and this is called a duet because it's 2. So this is an octet, this is a duet, this is a duet, because they can only hold 2 electrons. Although most covalent molecules follow the octet rule, some exceptions occur. For example, the element boron often forms covalent compounds that have an incomplete valence level. Notice in the structure, the boron only has 6 valence electrons, and it's very stable like that. There's always exceptions to the rule, and these are where we're going to start covering them. Boron wants to only have 6 around it, and it's stable like that. A more common exception occurs with larger elements. The nonmetals in rows 3 through 6 of the periodic table sometimes form bonds that result in an expanded octet containing more than 8 electrons. This is possible because of the d sublevels and the higher energy levels can accommodate extra electrons. Expanded octets often contain 5 or 6 covalent bonds. For example, phosphorus commonly forms 2 compounds. Either we have phosphorus with 3 chlorines, so phosphorus trichloride, or we have phosphorus with 5 chlorines. The phosphorus atom has a complete octet. In the second compound, phosphorus has an expanded octet with 10 valence electrons. And so you can see here, it can handle this, or it can also handle this. 2, 4, 6, 8, 10. Okay, so drawing a Lewis structure. By the way, I'm going to put up my own video on how to draw a Lewis structure. It's not in the books. I learned it outside of a book in a study guide, and it works, and it may not sound right, but it works well for the first 2 rows, which are in a periodic table. It's this row and this row, which you don't think, okay, it's only 2 rows. The thing is, most of what we use, the elements are in this row. We use most of these here and these here. So you can use it past in row 3 and on, but it's more of a guideline, and you have to keep that in mind. And why is it a guideline? Because once we start dealing with d orbitals, it's probably, in some of the cases it's resonance, which we haven't really covered yet, so you're not sure what resonance means. But resonance is, some compounds don't take one form, they take several forms. And it can probably provide you one of those forms, but you'd have to figure out the other forms. But it's a guideline. It's not mandatory to see, but I'm going to put it up. In some cases, I apologize, my dog. But it's a shortcut that I learned as a student, and it really did help me with a lot of this part where students have trouble with. So I strongly suggest you watch my video. Even if you don't use it, it could help in some ways, I think. But it's not mandatory. But I'm going to put it up because I learned it in a study guide. It always helped me. Okay, so let's get back to this. Okay, to understand how covalent compounds behave, we often need to understand their structures. The following 4-step process will help you draw Lewis structures from molecular family. First, you add up all the valence electrons. Use the periodic table. You determine the number of valence electrons for each atom, and you add them up. All of them. Recall that the main group atoms, group numbers, tell us the number of valence electrons in each main group element. Frame the structure. Use single bonds. Typically, the atom that is near to the lower left of the periodic table is the central atom. So what it's saying is over here. We haven't also covered electronegativity, which is when, and that's going to come up too. It's some atoms have a stronger pull on electrons than others, like a tug of war or sharing a blanket. And the nonmetals, the ones that are stronger tend to be here. So if you have something that's in front of it, that tends to be the center atom compared to the stronger ones. The stronger ones like to be on the outside. That will make sense when we get to that, and I'll bring it up again. So what they're saying is that if you have a bunch of elements, the ones that tend to be on closer to this side are the ones that tend to be in the center. Okay, so that is near the lower left of the periodic table is the central atom, and you try to keep these symmetrical. You want to keep them looking as symmetrical as possible, because it can only hold. Okay, and then hydrogen is never a central atom because it can only hold 2 electrons, so it'll never be. So if you have a carbon and 4 hydrogens, carbon's automatically going to be in the center because hydrogen can never do more than 1 bond. Fill the octets. So you fill the octets of the outer atoms first. Add lone pairs to the outer atoms to complete their valence levels. Fill the octet on the central atom. After filling in as the octets on the outer atoms, place any remaining electrons on the central atom. These electrons may be enough to fill the octet on the central atom, and may even result in expanded octet. If the central atom does not have at least 8, then you move electrons to create a double or triple bonds. This is where my shortcut video that I'll put up, if it's in the rows of 1 and 2, the steps that I use pretty much tell you if you have double or triple bonds, and it tells you how many electrons you have for a lone pair. It's just simple math, but like I said, it applies for the first 2 rows. And then it can help you set up a compound for through rows 3 and on, because the way I'm explaining here, this sounds really overwhelming at first. It does. I get that. Okay, so let's look at an example. All right. Let's draw nitrogen trichloride. So this is in the book. We can solve this problem carefully by the 4-step process. First, we add up the electrons. So you can see 5 plus 3, we have 3 chlorines that have 7. So that equals 26 electrons. So add up the electrons, and we can see the nitrogen has 5, chlorine has 7, but there's 3 of them, so 26. I already read that. Draw the framework. So what I mean by symmetrical is, since nitrogen, if you see nitrogen, chlorine's here, but nitrogen's further towards where the metals are. So this was going to be the symmetrical. Another indicator is that you have 3 of these. So which one do you put in the middle? And you don't know. So usually you put the one that's by itself in the middle. Unless it's a hydrogen, we don't do that. So as you can see here, we have a nitrogen in the middle. And so nitrogen is because it's left of chlorine on the periodic table. Then you connect the nitrogen to the other chlorines, and we use dashes. And remember, dashes represent 2 bonds. So as you do this, you can start subtracting 2, 4, 6. You could take 6. Now you have 20. Then you can start filling in everywhere. And if you have 2 more left, then you have to make the decision, is it a double bond or is it a lone pair? All right. So we fill the octets of the outer atoms first. So what they're saying here is, actually, I do it a little different, but they're saying to fill the lone pairs, because then it'll help you determine how many you have left for a bond if all of these are filled, because we don't touch lone pairs. They stay there. To complete, okay, so then we add 6 atoms, we add 6 more electrons to each chlorine. Fill the octet on the central atom. So we use 24 of the 26 valence electrons to complete the octets around chlorine. Now we've used the remaining 2 on the central atom. Notice in the Lewis structure, all 26 electrons are filled and each has an octet. So if we do 2, 4, 6, 8, that's an octet. 2, 4, 6, 8, that's an octet. 2, 4, 6, 8, 2, 4, 6, 8. So let's take a look at another one. Now we have formaldehyde. And it's commonly used in manufacture practices, plastics. I think they used to use it in mortuaries, embalming too. I could be wrong, but I'm almost positive they did. Draw the Lewis structure. So in the previous example, it's the same thing. We're going to sum up all the valence electrons. Chlorine has 4, hydrogen has 2, and oxygen has 1. And then from there, we have 12. So then carbon tends to be, so here we go. We're not going to use hydrogen. Hydrogens are never going to be, they're bookends. Remember, think of them as bookends. They're always bookends, or they're attached in kind of in a line, but never in the center. So carbon is going to be the center. In most cases, I'll tell you, carbon's usually the center one. Carbon is here. This is row 2. Remember I told you you tend to use row 2 a lot. So in the shortcut I'm going to show you, that's why. We tend to use all of these. So carbon is closer to the left of oxygen. So that's one other reason. This is more electronegative, which is a word you guys haven't used yet. But you'll find out what that means. And then we now can start adding up the electrons. So we don't add any lone pairs to hydrogen because we filled the duet. Then we fill out here, and then that leaves us with an octet. So if we have another pair, so we have 2, 4, 6, 8, that's octet, that's a duet, 2, 4, 6, 8, excuse me. This is showing you, I don't like how they showed this, because yes, what they're showing is true, but we haven't really covered how to do this. So let me explain a little bit. I don't like that they did this. For oxygen, we draw 6 additional electrons to complete its octet. So what it's doing is that, don't pay attention to this line or this arrow. This is, you see it, the line looks a little different because this is the actual bond here, this one line, and that represents 2, right? So 2, 4, 6, 8, it's an octet. But what they're showing you can happen is that this electrons come down and it creates a double bond. And that then leaves 2 electrons up here, 2 pairs. And that means 2, 4, 6, 8. This you'll learn later, and it's something you'll definitely learn if you're taking organic, because this happens a lot. But for the time being, What they want you to know is that there's a double bond here, and that's what could happen. But if you left it with just this, unless it's specifically stated a certain way, it would be fine. I don't like that they did that. All right, so let's go over the octet rule. Atoms are stabilized by having 8 electrons in their valence shell. And here's some examples. So we have a single bond, a double bond, and a triple bond. Now, if you watch my video will show you how to do all of these without trying to figure out where electrons go. It's actually quite easier. But again, not everybody wants to see another video. I completely understand. Do these atoms fill the octet? So let's take a look here. All right, we have, let's just show this one and we'll go through it. So carbon has 4 bonds. We have 1, 2, 3, 4. So this is what they're trying to say that oxygen looks like. If you move, to pretend this one bond's not here where my arrow is, it has 1 bond and then it has 6. But these electrons can move down, and when it moves down, it looks like this. That's what I was trying to say, but probably didn't explain it well. Okay, so let's look here. Carbon. Carbon has 4 bonds. 1, 2, 3, 4. So we got 4 bonds. Nitrogen. 1, 2, 3. So we have 3. And then, and it's saying that this is symmetrical. Remember I told you symmetrical, meaning one side looks very similar to the other. Think of it as a balance. If it's balanced, it's going to be stable. When things are not balanced, that's when they're unstable. And chemistry is all about lowest energy, the best stability. Oxygen. 1, 2, 4, 6, 8. So, but it's saying bonds, excuse me. Bonds has 2. And then hydrogen has 1. All of them have 1. Okay, so now let's go to carbon. So carbon has 1, 2, 3, 4, and it has 0 lone pairs. And that makes sense because carbon can't have more than 4 bonds. And then that means that we have 2, 4, 6, 8. It has 8 valence electrons. So let's look at nitrogen. And all we have to do is look at 1 because they're symmetrical. We have 3 bonds. We have 1 lone pair. But we have 8 valence electrons. 2, 4, 6, 8. And hydrogen has 2. So, and no lone pair. So this, we can see which ones all fill the octet and then which one fills the duet, even though they all look different with their bonding. Okay, so draw a Lewis structure. So these are again, a list of how to do that. And remember, it tells you the valence electrons. This is 1, this is 2, this is 3, 4, 5, 6, and so forth. Okay, so let's draw these Lewis structures. You want to sum up the electrons. You want to make it as symmetrical as possible with the atom that's closest towards the left, towards the metals, as the center. And then you want to fill in the electrons. So I'm going to I didn't do this by steps, but C would be the center. I mean, we already covered this one. But then you would start filling out electrons around it. And here, C is the center. But you can see one's got a double bond and one's got a single bond. And that happens. And we'll cover that in a little bit. But this is exactly what happens. One may not always be as symmetrical as the other. This is resonance, and you'll see what resonance means coming up. I don't want to throw any more at you. How many valence electrons are in phosphorus trichloride? So let's take a look at, first of all, what phosphorus trichloride looks like. We have phosphorus has 5, chlorine has 7, but there's 3 of them, so 26 is the answer. How many valence electrons are in cyanide ion? So, I forgot to show, I apologize, I meant to pull what it looked like here, and I didn't put that. So this one's a little strange, and I apologize for not putting it up. It is a carbon, if you can follow my mouse a little bit, and it's got triple bonds. So imagine triple bonds in between these. But if you count the triple bonds, that's only 6. So what it is that nitrogen has a lone pair, and carbon also has a lone pair. So you have 2 dots on the outside here, 2 dots on the outside here, and then 3 in the middle. So that's 2, 4, 6, 8, 10. 10 is the correct answer. Which of these is a correct Lewis structure for sulfur dichloride? So sulfur, because there's only one, I'm going to tell you that's going to probably be in the middle. It's left of chlorine. And then we have 2 dichlorides. So we're going to take a look and let's just see which one it is. And it's this one right here. Sulfur dichloride. How do you know this? A lot of it, there is no way of, there's not rules. And some of these you just have to actually write them out. And the more it's a repetitive nature of then eventually you start knowing what the formulas look like. I wish I had a better answer. You can set them up, and most of the time as you start doing them, and I'll be honest with you, a lot of chemistry, we use the same compounds over and over as we're learning. So you usually don't get really obscure ones unless that teacher really has a vast knowledge of other compounds. What is the Lewis structure of CS2? So this is sulfur dichloride, this is carbon disulfide, and as that was shown earlier in the PowerPoint, it's that one. How would you know that? Well, you could look and you can start seeing how these look and count the electrons and see if any of these go past. This one I can tell you, carbon doesn't have 2 lone pairs. It just doesn't. It can hold 1, but it can't do 2. Not in this level of chemistry. And you can just start counting and you can see this is way not happening. That one doesn't even exist. How many lone pairs of electrons are on the central atom in the chloride ion? So if we look at the chloride ion, we see we have 1 lone pair. But oxygen has 3 oxygens, 2 have double bonds, and 1 has a single bond. Draw a Lewis structure for the triiodide ion. And notice this is going to be 3 iodides then. And how many lone pairs? So if we do this, write this out, you should be able to see that this has 2, 4, 6, 8, 10. It actually has 3 lone pairs on it. And that's because what makes these harder to understand, and this is how they're being introduced. So this may seem overwhelming, but this is where the repetitiveness comes in. We introduce you to them, you start learning these, and you'll see them over and over and over again. This is either in row 3 or down, which means it has D sublevels, and that's when it starts making these things kind of kooky looking from what